Hi everyone, this is Vivek Gupta. Welcome to my presentation. Today I am presenting on RetroNLU, Retrieval Augmented Task Oriented Semantic Parsing. This is a work done with Facebook. The takeaway of my talk is, in this work we explore a method called RetroNLU, which is a retrieval based modeling approach for task oriented semantic parsing problem. RetroNLU make effective use of retrieve examples of semantic parse. This can be from the training data or some other source that model learn to adapt for other similar input instances. We analyze the robustness and sensitivity of our RetroNLU work across several dimensions, mainly on the side of data efficiency, how it works for limited supervision setting, how robust is the retrieval with noise, is the model perform well for complex utterances, and how well is the knowledge with respect to the knowledge efficiency, how many knowledge we need to add to make the model much better. So let me first introduce the task-oriented semantic parsing. So here the task-oriented semantic parsing, you are given an utterance. For example, here is like please add 20 minutes on the lasagna timer. Now semantic parse basically add intent and slot along with slot values which is coming from the utterance to the task. For example, here the intents are mainly add time timer and the slots which is concerned with is the date time and the timer name and also the method name, like what timer we want to address. So this is coupled representation. There are also some words which are now not useful. For example, like please add on the, because we already know the intent and only the slot value which is important, which is coming from the utterance, is there. Like for example, lasagna timer 20 minutes. So we can also remove these words and make the representation bit more clean. So this is called decoupled representation of the SEM parse. So the task oriented parsing task is basically you are given a utterance, so you have to convert it into a semantic parse which has intent and slot. Now this intent and slot can be hierarchical, so there can be intent slot followed by intent, so there can be multiple intent in this. For example, in this example which is shown in the right, this is taken from the top data set. So as you can see, this is a structured prediction complex task. So the technique which we want to apply is retrieval augmentation. So the idea is, so we are given this task of doing converting utterance to its SEM parse, which is the parse which I show you. Now we have our nearest neighbor index built on a source or data set where we already know which utterance is mapped with which parse. This can be even your training set. Now you take the utterance which you have and try to find the nearest neighbor of it in the same set. Obviously we don't take neighbors which are exactly same, we take neighbors which are different in utterances but have similar intent and slots. So here we do not use the label data, we just capture similarity between the utterances using a pre-trained BART model. Once you get the utterances, you take the nearest neighbor context. In this we are taking the SEM parse of this, which we found it's better. You can even take the utterance of it. And then what you do is you augment this SEM parse with the utterance as an additional context in the beginning. And now instead of solving the initial task where you are given an utterance to convert to SEM parse, you basically have a nearest neighbor SEM parse plus the utterance, and the whole thing is converted to a SEM parse. You use this also for training as well as retrieval setting. Let me give you an example of this. For example, the same thing, please add 20 minutes on the lasagna timer. The expected SEM parse is shown. Now I get the nearest neighbor utterance, which is add 10 minutes to the oven timer. Now I get the nearest neighbor SEM parse, which is given in the training data itself. And now what you do is the final utterance will be a combination of this SEM parse plus the extracted SEM parse. And now so you nearest neighbor SEM parse is added with the original initial utterance, and the task is again to get the expected SEM parse. So this is how we do a retrieval augmentation. So this is a flow chart which quickly depict this. So you have this example utterance, you have source utterances. This can be from the training set as well as some other source. And now you basically extract features. Then you basically do a encoding and build the nearest neighbor indexes of these. This nearest neighbor indexes you can build by FAST or another library. So this complete the indexing phase. Now for utterance which is given, you have to find basically its nearest neighbor. You can get this from retrieval using a FAST or FAST library of retrieval. Once you have this, you can basically append this utterance with either the nearest neighbor utterance, or you can even use the SEM parse of that nearest neighbor to append. And once you have appended that with the SEM parse or the utterance nearest of the nearest neighbors, you can basically pass the whole thing as an input context to an encoder decoder architecture. and this is a sequence to sequence architecture, and finally you get the output SemParse which we are looking for. This is the last pass of semantic parsing. Now we use top V2 datasets. I won't go in detail. So this dataset has a large variety of hierarchical, complex compositional utterances. It also has the source and the target domain. In this work, we primarily deal with the source domain, and it has shown in the previous work where this dataset was introduced that it has high capacity to check even low resource domain adaptation, which we kept as a future work. So in this mainly we deal with the source domain, which has 5 main target domains: alarm, event, music, navigation, and timer. So let's look at the primary questions we answered in this paper, in this work. So first we look at data efficiency. So we want to see if this method effective. Can this retrieval based method, which take non-parametric external knowledge, elevate some reliance on the parametric knowledge which is which is acquired using training on large supervision data? So can we get away with some of those knowledge by using this nearest neighbor or non-parametric retrieval knowledge? So in this, what we did is we perform result analysis on 2 settings: supervised and unsupervised setting. Where supervised we have lot of labeled data, and unsupervised we have limited labeled data. We have lots of unlabeled data. So we found that in the supervised setting our model actually outperformed. It outperformed not only on average macro and micro F1 score. It's also outperformed the baseline, which was not using retrieval on all domains except a bit improvement in the timer domain. So it's so huge improvement in some of the domain like alarm, messaging, and navigation, where similar instances were there. So we found that few patterns also. First, when we applied this method, we found that we were not getting so much improvement in performance. So we found that there were duplications in the training sets, which we removed when we are doing the retrieval. We also tried to see if increasing the nearest neighbor, instead of adding only one nearest neighbor, if we add more nearest, does it help? So we found that it helped, but the performance is still not improving drastically. And one possible reason of this is maybe there's no diversity across the nearest neighbor. So this is the future work we are looking for. How can we increase diversity in the retrieval aspects? We also tried unsupervised approach, where for example you have the source thing where only utterances are given. You don't have the corresponding SemParse. So this is not a training set. This is just unlabeled example set which you are given. In that you can just append the utterance. The whole procedure will remain same. The only thing which will be there is basically you append the utterances which is there. We found that this approach actually can work because there can be cross contrastive learning. So I won't go in details, but the idea is basically like there can be utterances which are neighbor of each other, and they can basically pass or transfer information about SemParses across things. So for example, in this we know that please add 20 minutes to the Lasanga timer, add 10 minutes to the oven timer can be nearest neighbor of each other, and that's why their parse will be similar to each other, and this information can basically transfer in the unsupervised setting. I encourage people to read the paper for more details. In the unsupervised setting, we found that we got improvements. Obviously, the improvement was not as good as compared to the supervised setting, as you can see. But we found on some domains where it was not doing that well in the supervised setting, it started to do much better. But other domains obviously not performing as good. So we found around 0.5 to 0.6% less improvement with this unsupervised approach, but it was still doing better than no supervision approach or no retrieval based approach. Sorry. So this was the overall, like without NNN we are getting around like 84 something, and with supervision we are able to get around 84.5, and with utterance only thing, utterance based nearest neighbors, and with SemParse based nearest neighbor we are able to cross even 86, around 87, 86. So we can see this trend. Obviously the similar trend was there for 2 nearest neighbor, 3 nearest neighbor. However, the gap has increased, the number of nearest neighbor decreases even between supervised and unsupervised approach. So next we look at how limited supervision can help. So for example, now we have a lot of abundant and inexpensive unlabeled external parametric knowledge. So for example, you have labeled data or unlabeled data on the source indexing, but you don't have that for the training, and this can be constrained because you want to employ the model fast, or you are basically limited with the compute on which you can train on or the time you can train on. In this setting, or maybe the examples are also less. So we see if this nearest neighbor approach can really help in that case, and we found this by using semi-supervised thing, and this can have lots of updates, like it can be used for unlabeled data, it can be used for incrementally updating the model without much training in the parametric side, using large which uses large data, labeled data and all. So we found this trends. First of all, like obviously with increasing training data, the model performance improve. But in all setting, even in low resource setting, the SEMPAS and the utterance NS are doing much better. So we found that the gap, less data, obviously the accuracy are lack. We found that we are able to use the original performance with just 40% of the original data. So we can remove 60% of the data and still we can do much better. And this is just random sampling. This is not strategic sampling or something smart way of sampling. So if we do that, maybe we can even reduce the data dependence much more with this approach. We also found that utterance perform as good as SEMPAS in low data regime. We also find that the relative gain as you have more parametric knowledge is lesser. So for example, 10% you see huge improvement between without nearest neighbor and with our approach of retrieval augmented nearest neighbor. But as you go with 100 and beyond 50 to 100% data, the gap drastically started reducing. So the gain you get is not that significant. For example, at 10% you are able to get 4.2% gain versus getting only 1.3% in the 100%. Last, we did a lot of analysis on the retrieval side, like how does retrieval quality, how does simple and complex utterances have performance improvement, and how frequency of utterances affect the this method. So first we look at noise robustness. So basically the main aim is like, is this approach we applied and it looked for nearest neighbor retrieval, and if the nearest neighbor retrieval is not that resilient to noise. For example, if the nearest neighbor retrieval has erroneous retrieval, so can still the parametric knowledge be used for making the prediction correct? And we found this is true. So for doing this, what we did is we basically have, without NNN, we have the best first nearest neighbor, and then we take totally random cross domain nearest neighbor and one neighbor from the random top 100. So it can be anything from the top 100. So we found that even with the random 100 top neighbors, it's doing pretty good. And even with the cross domain, it's basically starting to use the right nearest neighbors and getting performance. Obviously, with best nearest neighbors doing pretty good. We found that utterance nearest neighbor started failing when you start using cross domain, which is kind of expected because now you are adding examples of totally different things. But in the SEMPAS, it still improve, and this I feel is because of the same reason as the unsupervised label approach was happening, like cross domain contrastive learning. You can see the paper for more details on this. But they show that the model is quite robust. For example, in random top 100 is still performing good, and even with cross domain, at least in the SEMPAS setting, is doing pretty good. Obviously, the gain is marginalized, but it's good. And we suspect this is happening because there is already a noise in the training set, which is making the model resilient. We also did one experiment where we take the golden SEMPAS kind of thing, which matches much more with the gold parse, and there we use that for training, and we found that model is actually not very resilient to noise. So that means having noise in the nearest neighbor while training itself is beneficial, which is automatically happening when you use this approach. We also look at utterance complexity. Basically, is this approach even beneficial for complex utterances, or it's just useful for simplex, and how much is which type of utterance is beneficial more? So complex utterances, as I already do, like they have more intent, like they have hierarchical intent structure. So there is hierarchical nesting. So in the top V2, we actually look at this complex structure. So this was not present in the top data set, but the version 2 has those. And there are around 15% which has up to 2 level, like 2 intent, and there are more than 3 intent for 2.7%. So roughly around 18 to 19% of the data has more than depth 2 to 7. So we did this analysis of simple versus complex. Simple is depth 1 and complex is 2 and beyond. We found that obviously simple is easy to classify, and the performance first is more for the simple data. But the gain which we get from the complex is much more higher, and we also found that the utterance NN doesn't work much well for the complex data, which is kind of expected. But the simple NN, but the SEMPAS nearest neighbor approach really work well for the simple data. We also expect this is because also rareness of the thing, which we also analyze later, as well as the complexity involved in using multiple intent, which is not easily coverable with the utterance only nearest neighbor. So there the SEMPAS nearest neighbor is very beneficial. This also show like if you have domains which are difficult and harder and have multi-intents things, it's better to have their label data in the parametric knowledge rather than using unsupervised more approach in this case. We also did a retrieval analysis. We found that the precision was pretty okay. The model obviously was doing worse in all cases for the complex, both precision and recall in the retrieval setting, but majorly it suffered because of the recall in this, and this can be something which we can look in the future of how we can improve the recall and make the model much more better. So slot retrieval was much more improved than the intent, which is expected because the intent is limited and slots are much more than the intent. But there can be some structure constraints which can be put to make this work, which is we are leaving for the future work to explore. We also find that did analysis on rare versus frequent. So there we form equal buckets into 5 parts of high frequent to low frequent. Each one has equal number of examples for a fair comparison, and then we basically do this without NNN and with NNN, SEMPAS and utterance based only augmentation. We found obviously with high frequency when the performance was also large, plus the improvement was also not that significant, but performance increases quite significantly for the lower domain. So we get the relative performance improvement very significant for the low frequency thing. So this is again similar to the last thing where we show the improvement which we get for complex utterances is much more, although the performance overall of them is pretty low. So the gap is also very large there. We also did retrieval analysis and similar patterns was obtained there, which I won't go in detail, but as you can see in the paper also. Lastly, we look at knowledge efficiency, basically where are the boundaries of this thing and where it can go. So we found that if we add much more nearest neighbors, the addition of nearest neighbor is not really helping things. So pre-trained BART embedding is good, but it's not that effective also. So we found that the performance of retrieval was roughly close to 85%. So it was a little bit more for the valid and the test set. We also found that adding nearest neighbor is not that much helping, and the later nearest neighbor are not good as the initial nearest neighbor. And we also find that maybe bringing diversity or some other factors in retrieval could be interesting, which we have left in the future work. You can see the discussion section in the paper for more ideas on this. So I will again go away with the takeaway. So we explore this method RetroNLU, which is a retrieval based complex approach for task oriented semantic parsing problem, which is a complex structure prediction task. We use explicit use of retrieval based memory from augmented examples, which model adapt for similar input instances. We analyze the RetroNLU across several dimensions of data efficiency, limited supervision settings, robustness to retrieval noise, how does it perform for complex versus simple utterances, as well as in terms of knowledge efficiency of how nearest neighbors are helping and where they are not helping. So these are some of the examples. I will invite you all for the poster session as well as the oral presentation to ask me more questions about this thing. Thank you all.